From the smallest atom to the largest galaxy, the universe is a vast and mysterious expanse. It beckons us to explore its depths, to unravel its secrets. Join us now on a cosmic journey, a voyage through space and time. Let us set our sights on the universe itself, seeking to understand our place within its grand design. Our journey begins with a fundamental question. How did it all begin? What sparked the creation of everything we see around us, the stars, the planets, even ourselves? The answer, as far as we understand it, lies in an event of unimaginable power and scale, the Big Bang. This is not merely a tale of distant stars and galaxies. It is the story of our own origins, a quest to understand the very fabric of reality. So fasten your seatbelts and prepare to have your mind blown as we delve into the wonders of the universe. Imagine, if you will, a time before time itself, a point where everything we know was compressed into a singularity, an infinitely dense and hot point. Then in a fraction of a second, everything changed. The Big Bang occurred and the universe as we know it burst into existence. Space itself expanded at an incredible rate, carrying with it a sea of energy. As this energy cooled, it began to coalesce, forming the first elementary particles. These particles, the building blocks of matter, came together to form the first atoms, primarily hydrogen and helium, the simplest elements in the universe. Over eons, gravity, the architect of the cosmos, drew these atoms together, forming vast clouds of gas. These clouds, under their own gravitational pull, collapsed further, igniting the nuclear furnaces at their cores and giving birth to the first stars. These early stars, massive and short-lived, became cosmic factories, forging heavier elements in their fiery cores. As they reached the end of their lives, they exploded as supernovae, scattering these newly created elements across the cosmos. From these stellar remnants, new generations of stars and planets would arise. Our own solar system, including the Earth we call home, is a product of this cosmic recycling process. The atoms that make up our bodies, the air we breathe, and the ground beneath our feet were all forged in the hearts of distant stars. Our journey is far from over. Join us as we delve deeper into the universe's mysteries, exploring the fundamental forces that govern its behavior and the enigmatic substances that shape its destiny. The Big Bang wasn't an explosion in the traditional sense. It wasn't something happening in space, but rather the expansion of space itself. Imagine a balloon with dots drawn on it. As you inflate the balloon, the dots move farther apart, just as galaxies are doing in our expanding universe. This expansion continues to this day, a testament to the Big Bang's enduring legacy. And just like the fading heat from a bonfire, we can still detect the faint afterglow of that initial event, a cosmic echo that permeates the universe. This afterglow, known as the cosmic microwave background radiation, is a faint whisper of light stretched out over billions of years, telling us a story of the universe's infancy. It provides a glimpse into a time when the universe was a hot, dense soup of elementary particles, a time long before stars and galaxies graced the cosmos. As the universe expanded, it cooled, allowing particles to combine and form the first atoms. This marked a pivotal moment in cosmic history, the era of recombination, when the universe transitioned from an opaque fog to a transparent expanse. This transparency allowed light to travel freely for the first time, bathing the universe in a warm, diffuse glow. It's this light, redshifted over eons into the microwave part of the electromagnetic spectrum, that we detect as the cosmic background radiation. This radiation isn't uniform. It contains subtle temperature fluctuations, tiny ripples in the fabric of space-time that provide clues about the seeds of galaxies, the very structures that would one day light up the universe. These fluctuations, like brushstrokes on a cosmic canvas, hint at the intricate processes that shape the universe we observe today. Studying the cosmic background radiation is like peering back in time, to an era just a few 100,000 years after the Big Bang. It allows us to probe the conditions of the early universe, its temperature, density, and composition. The remarkable uniformity of this radiation across the sky suggests that the early universe was incredibly homogeneous, a finding that supports the Big Bang theory. However, those tiny temperature fluctuations, those subtle imperfections, are equally important. These fluctuations, amplified by gravity over billions of years, gave rise to the large-scale structures we see today, the clusters, superclusters, and filaments of galaxies that make up the cosmic web. They are echoes of the quantum fluctuations that existed in the universe's earliest moments, stretched out across vast distances by cosmic expansion. Within the expanding universe, gravity began to sculpt the cosmos. It drew matter together, forming vast clouds of gas and dust. These clouds, under their own gravitational pull, collapsed further, eventually igniting to form the first stars. These early stars, massive and short-lived, clustered together, drawn by gravity's inexorable pull to form the first galaxies. These galaxies, much smaller and more irregular than those we observe today, were the building blocks of larger cosmic structures. Over billions of years, galaxies collided and merged, growing larger and more complex. Our own Milky Way galaxy, a spiral behemoth containing hundreds of billions of stars, is the product of countless such mergers, a testament to the enduring power of gravity in shaping the universe. The early universe was a turbulent and chaotic place, a cosmic nursery where stars were born and galaxies took shape. It was a time of intense star formation as vast quantities of primordial gas and dust coalesced under gravity's influence. These early stars and galaxies emitted intense radiation, ionizing the surrounding gas and shaping the intergalactic medium. This era, known as the Epoch of Reionization, marked a profound transformation in the universe's evolution. As the universe continued to expand and cool, the rate of star formation gradually declined. Galaxies settled into their familiar forms, spirals, ellipticals, and irregular, their evolution governed by the interplay of gravity, gas dynamics, and stellar feedback. The stage was set for the emergence of more complex structures, including planets and eventually life itself. The universe is far from a static and unchanging place. It is a dynamic and ever-evolving realm, shaped by a delicate interplay of forces. These forces, the fundamental laws of nature, govern the interactions of matter and energy at all scales, from the smallest subatomic particles to the largest cosmic structures. At the heart of this cosmic dance are four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces, though seemingly disparate in their effects, are intricately interwoven, their interplay giving rise to the universe we observe today. Gravity, the weakest of the four forces, yet the most familiar in our everyday lives, is responsible for the large-scale structure of the universe. It's the force that draws mass together, shaping galaxies and holding planets in orbit around stars. Electromagnetism, on the other hand, governs the interactions of electrically charged particles, binding atoms together and giving rise to light and other electromagnetic radiation. Gravity, despite its weakness, plays a pivotal role in shaping the universe on the grandest scales. It's the force that caused the early universe to clump together, forming the seeds of galaxies. It's the force that holds galaxies together in vast clusters and superclusters, weaving a delicate tapestry across the cosmos. Without gravity, stars and planets would never have formed. The immense pressure at the centers of stars, generated by gravity's relentless pull, is what ignites the nuclear fusion that powers these celestial furnaces. Gravity also dictates the life cycle of stars, from their formation to their eventual demise. Gravity's influence extends even beyond the realm of visible matter. It's the force that governs the behavior of dark matter, a mysterious substance that makes up the majority of the universe's mass. Dark matter, though invisible to our telescopes, interacts gravitationally with visible matter, shaping the distribution of galaxies and influencing the cosmic expansion rate. Section 4. The quantum realm. While gravity and electromagnetism dominate the macroscopic world, the quantum realm, the realm of the very small, is governed by the strange and counterintuitive laws of quantum mechanics. In this bizarre realm, particles can exist in multiple states at once, and the act of observation can influence the outcome of an experiment. Quantum mechanics is essential for understanding the behavior of matter at its most fundamental level. It explains the properties of atoms and the interactions of particles within the nucleus. It's also at the heart of many technological advancements, including lasers, transistors, and magnetic resonance imaging, or MRI. One of the most intriguing aspects of quantum mechanics is the concept of entanglement, where two particles become linked, even when separated by vast distances. This spooky action at a distance, as Einstein famously called it, has profound implications for our understanding of the universe and could pave the way for future technological breakthroughs in quantum computing and communication. Section 5. The dance continues. The interplay of these fundamental forces, from the cosmic ballet of gravity to the intricate dance of quantum particles, shapes the universe we observe today. It's a dance that's been ongoing for billions of years, a dance that continues to this day, driving the evolution of stars, galaxies, and even life itself. As we delve deeper into the mysteries of the universe, we uncover new layers of complexity, new insights into the fundamental laws that govern its behavior. But with each discovery, new questions arise, pushing the boundaries of our understanding and inspiring us to explore further. The universe is a vast and enigmatic place full of wonder, beauty, and endless possibilities. As we continue our cosmic journey, we carry with us the knowledge that we are part of something far greater than ourselves, a cosmic dance that began with the Big Bang and continues to unfold before our very eyes. Our cosmic journey takes us now into the realm of the unseen, to the mysterious substances that dominate the universe yet remain shrouded in enigma. We delve into the depths of space, where gravity's pull hints at the presence of something massive, something invisible to our most sensitive telescopes. This is the realm of dark matter and dark energy, two of the most profound mysteries in modern cosmology. These enigmatic entities, though invisible to our eyes, hold the key to understanding the universe's structure, its evolution, and its ultimate fate. Dark matter, like an invisible hand, sculpts the cosmic landscape, its gravitational influence shaping the distribution of galaxies and influencing the cosmic web's delicate tracery. Dark energy, even more perplexing, acts as an anti-gravitational force, driving the universe's accelerated expansion, pushing galaxies apart at an ever-increasing rate. The first hints of dark matter's existence emerged in the 1930s, when astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving faster than they should have been based on their visible mass. Something unseen, something massive, was providing the extra gravity needed to hold the cluster together. This invisible mass, dubbed dark matter, doesn't interact with light or other forms of electromagnetic radiation, making it impossible to detect directly. However, its gravitational effects are undeniable, leaving an indelible imprint on the cosmic landscape. Observations of galaxy rotation curves, the way stars orbit around their galactic centers, provided further evidence for dark matter's existence. Stars in the outer regions of galaxies were observed to be moving much faster than they should have been based on the visible mass alone, suggesting the presence of a halo of dark matter enveloping each galaxy. While dark matter's gravitational pull binds galaxies together, dark energy acts as a repulsive force, pushing them apart. Its existence was first inferred in the late 1990s, when astronomers discovered that the universe's expansion, long thought to be slowing down due to gravity, was actually accelerating. This discovery, which earned the 2011 Nobel Prize in Physics, revolutionized our understanding of the universe's evolution. It suggested that the universe is not only expanding, but it's expanding at an ever-increasing rate, driven by a mysterious force that counteracts gravity's pull. The nature of dark energy remains one of the biggest mysteries in modern cosmology. Some theories suggest that it's a property of space itself, a cosmological constant that Einstein first proposed and later discarded. Others propose the existence of a new type of energy field, dubbed quintessence, that permeates the universe and drives its accelerated expansion. Section 4. Unraveling the dark side. Scientists are actively pursuing a variety of avenues to unravel the mysteries of dark matter and dark energy. Particle physicists are searching for new particles that could make up dark matter, conducting experiments in underground laboratories and using powerful particle accelerators to smash atoms together, hoping to create these elusive particles in the lab. Astrophysicists are studying the cosmic microwave background radiation and the distribution of galaxies for clues about the nature of dark matter and dark energy. They're also using gravitational lensing, the bending of light around massive objects, to map the distribution of dark matter in the universe. New telescopes and observational techniques are constantly being developed, promising even deeper insights into the dark side of the universe. The James Webb Space Telescope, launched in 2021, is expected to revolutionize our understanding of the early universe and provide valuable data on the nature of dark matter and dark energy. Section 5. The Cosmic Web, a tapestry of light and darkness. Dark matter and dark energy, though invisible, shape the universe we observe today. They form the scaffolding upon which galaxies are built, weaving a vast cosmic web. Dark matter's gravitational pull draws matter together, forming the filaments and nodes. Dark energy's repulsive force pushes galaxies apart, creating vast voids. This interplay between light and darkness has shaped the universe's evolution. As we explore the cosmos, we find a place of profound beauty and mystery. Section 1. Stellar nurseries, where stars ignite. Our cosmic journey now takes us into the heart of stellar nurseries, vast clouds of gas and dust where stars are born. These nebulae, as they're called, are some of the most visually stunning objects in the universe, glowing with an ethereal beauty as they cradle newborn stars. Within these interstellar clouds, gravity draws together atoms of hydrogen and helium, the primordial elements forged in the Big Bang's fiery crucible. As these atoms clump together, they heat up, their kinetic energy transformed into thermal energy, raising the temperature at the cloud's core. This process of gravitational collapse continues for millions of years, the cloud's core becoming increasingly dense and hot. Eventually, the temperature and pressure at the core reach a critical threshold, igniting nuclear fusion, the process that powers stars. Section 2. The life cycle of stars, a cosmic ballet. The birth of a star marks the beginning of a cosmic ballet, a delicate balance between gravity's inward pull and the outward pressure generated by nuclear fusion in the star's core. This balance, known as hydrostatic equilibrium, determines a star's size, temperature, and luminosity, dictating its fate over millions or even billions of years. Stars spend the majority of their lives fusing hydrogen into helium in their cores, releasing vast amounts of energy in the process. This energy radiating outward from the core counteracts gravity's inward pull, maintaining the star's stability. The length of a star's life depends on its mass. Massive stars, burning brightly and furiously, exhaust their nuclear fuel quickly, living for only a few million years. Smaller stars like our Sun live for billions of years, their slower fusion rates allowing them to sip their hydrogen fuel over eons. Section 3. From red giants to white dwarfs, stellar afterlives. As a star exhausts its hydrogen fuel, its core contracts, heating up further. This increased temperature ignites helium fusion, converting helium into heavier elements like carbon and oxygen. The star expands significantly, becoming a red giant, its outer layers engulfing nearby planets in some cases. Eventually, even the helium fuel is exhausted. Low-mass stars, like our Sun, shed their outer layers, forming planetary nebulae, glowing shells of gas illuminated by the dying star's core. The core itself contracts further, becoming a white dwarf, an incredibly dense object about the size of Earth. White dwarfs, no longer supported by nuclear fusion, slowly cool over billions of years, eventually fading into faint embers known as black dwarfs. These stellar remnants, composed mostly of carbon and oxygen, represent the endpoint for the vast majority of stars in the universe. Massive stars, however, meet a more spectacular fate. As they exhaust their nuclear fuel, their cores collapse under their own gravity, triggering a catastrophic explosion known as a supernova. These cosmic cataclysms, among the most energetic events in the universe, briefly outshine entire galaxies. Supernovae blast the star's outer layers into space, enriching the interstellar medium with heavy elements forged in the star's core. These elements, scattered across the cosmos, become the building blocks for new generations of stars and planets. The core itself, crushed by the supernova's immense force, forms either a neutron star, an incredibly dense object composed mostly of neutrons, or a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. Stars are not only the universe's luminous beacons, but also its cosmic alchemists, transforming the primordial hydrogen and helium forged in the Big Bang into heavier elements essential for life. This process, known as stellar nucleosynthesis, occurs in the fiery hearts of stars throughout their lives and during their explosive deaths. During their main sequence phase, stars fuse hydrogen into helium, releasing energy that powers their shine. As they age, they begin fusing helium into carbon and oxygen, eventually creating elements as heavy as iron in their cores. Supernovae, in their cataclysmic explosions, create even heavier elements, scattering them into space, where they eventually become incorporated into new stars and planetary systems. The very elements that make up our bodies, the carbon in our cells, the oxygen we breathe, the iron in our blood, were all forged in the hearts of distant stars. Our cosmic journey has taken us from the universe's fiery birth in the Big Bang to the majestic dance of stars across the cosmos. From the relentless pull of gravity to the enigmatic influence of dark matter and dark energy. We've witnessed the awe-inspiring life cycle of stars, from their birth in stellar nurseries to their explosive deaths as supernovae, forging the very elements that make life possible. As we gaze out at the vast expanse of the cosmos, we are filled with a sense of wonder and humility. The universe is a tapestry of breathtaking beauty and profound mystery. The quest to understand the universe is a journey without end, a journey that challenges us to expand our minds, to embrace the unknown, and to never stop asking questions. As Carl Sagan so eloquently put it, somewhere, something incredible is waiting to be known. So let us continue to explore, to question, to marvel at the wonders of the cosmos. For in the words of the great astronomer, the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. Join us as we continue to delve into the mysteries of the universe, to unravel its secrets, and to share the wonders of scientific discovery with the world. Subscribe to our channel for more fascinating explorations of science and the universe, and let us know your thoughts in the comments below.